Okay, so we're going to continue with Chapter 5, which is the chapter on energy. Yesterday, we talked about kinetic energy. And yesterday, we said kinetic energy is energy of motion. And the equation for kinetic energy was 1/2 mv squared. So that's what we did yesterday. Now, tonight, we're going to look at something called the work energy theorem. And some of the things we said yesterday about kinetic energy was examples: a coiled spring unwinds, dynamite explodes, battery used to make a toy run. So these are all things that are moving. Water behind a dam is released. A rock topples off a cliff. The work energy theorem says that work is equal to the change in kinetic energy. So if we rewrite this, we know that work is equal to FD. And the change in kinetic energy, remember, kinetic energy is 1/2 mv squared, so it would be 1/2 mvf squared minus 1/2 mvi squared. So this is just taking W, which is work, which is delta KE, and remember, delta is the final minus the initial, and then kind of expanding it out. So work is equal to force times displacement. Kinetic energy, the delta is the final minus the initial, and then kinetic energy is 1/2 mv squared, so that would be 1/2 mvf squared minus 1/2 mvi squared. So let's look at an example. The example says an 8-kilogram mass moves at 30 meters per second. So when we read these problems, again, we want to write our given, the 30 meters per second. What is the kinetic energy? If the object was initially at rest, so now I know that this is the final velocity, the initial velocity is 0, because it was at rest, how much work was done on the object to give it this kinetic energy? So kinetic energy is 1/2 mv squared, and so 1/2 the mass times the velocity squared. Now remember, in physics, we can always carry our units through to check our work. So when I square the 30, I'm also squaring the meter per second. So I have a meter squared over second squared times a kilogram. Well, what I'm going to do is I'm going to pull out the kilogram meter per second squared, which is a Newton, and then I have one more meter left, and a Newton times a meter is a joule, which is the correct unit for energy. Part B says how much work was done. Well, I know that work is equal to the change in kinetic energy, which is the final minus the initial. So the final kinetic energy I found right here, the initial kinetic energy is 0 because the velocity is 0. Because if I have 1/2 mv squared, if velocity is 0, anything times 0 is 0. And that's it. Now, in this chapter, we're going to be talking about mechanical energy. Is energy going to stop throughout the year in physics? No. As we go on, we're going to be talking about different forms of energy. In this chapter, we're just going to be talking about mechanical energy. But even when we talk about mechanical energy, specifically kinetic and potential, there's also different types of kinetic and potential energy. So here's some examples. So kinds of potential energy, we have atomic, which comes from radioactive materials. We know that in nuclear power plants, when you talk about thermonuclear fission, they split atoms to produce energy. And then we'll talk later on about energy transformations, how that energy is then transformed to other types. Other types of potential energy, chemical, that's what's stored in batteries. Energy gravitational, which exists between any two masses in the universe. That's what we're going to talk about a little bit today. Kinds of kinetic energy, heat that comes from the sun, mechanical energy in machines, and sound, which comes from vibrations. So potential energy is the energy that's stored in an object, or energy that an object possesses because of its position. So we're going to look at two types of potential energy in this chapter. Okay? Now, when we looked at the examples of kinetic energy, now we're going to look at the converse as far as potential energy. So now we have a coiled spring. When that coil spring unwinds, that potential energy is being transformed into kinetic. A stick of dynamite, so that energy is stored in that stick of dynamite. A fully charged battery, so the battery can then make a toy move, like the lab that we did earlier in the year with the little battery-operated cars. Water behind a dam, a rock sitting on top of a cliff. So first we're going to talk about gravitational potential energy. So this is the potential energy an object has due to its position above Earth's surface. Now in physics, whenever we have to measure anything, we always have to have a frame of reference. So for gravitational potential energy, the frame of reference is going to be the ground. But we're going to call the ground a fancier name. We're going to call it base level. So this is the position where the potential energy is chosen to be zero. And that, again, this is just another name for the ground. The equation for potential energy, gravitational potential energy, and we can call this PEG for gravitational, is mgh. It's mass times gravity times height. And again, the units for energy is always the same. So if we look at this, mass is measured in kilograms. This is meters per second squared. And then the height is meters. So a kilogram meter per second squared, that's a newton. And a newton times a meter is joule. So we're always going to measure energy in joules. So here's an example of gravitational potential energy. It says a 5-kilogram bowling ball is lifted from the floor to a height of 1.5 meters. What is the increase in the gravitational potential energy? So we're given the mass as 5 kilograms. We're given the height. So the change in potential energy, now on the ground, it would be 0. So remember, the change in potential energy, delta PE, is actually PEF minus PEI, but the initial would be 0 if I'm starting off on the ground, because the ground would be base level. So this is really the change in potential energy, and I didn't do the final minus the initial because the initial would just be 0. So it's the mass times the gravity times the height. So again, there's different types of potential energy, and each type is associated with a particular type of force. Now, there's potential energies that's also stored in a spring. Have you ever seen a jack-in-the-box, and you turn the little teeny crank handle, and then the jack-in-the-box like jumps up, and there's a spring. So what's happening there is you are turning the little crank, and that's stored in the spring, and that energy stored in the spring, there's actually several energy transformations taking place, and then it makes the jack-in-the-box pop up. So first, in order to understand the energy stored in a spring, we have to understand something about springs. So every spring has a different stiffness, like how stiff that spring is, and the stiffness of the springs. And when we do different labs, the reason why we use different spring scales, like the last lab we did on friction, remember we had a spring scale that only went to 2.5 newtons, and then we have other spring scales that go to 10 or 20 or 50 newtons because those have stiffer springs. So every spring has a certain stiffness, and the stiffness of the spring is called the spring constant. So we can measure that using something called Hooke's law. Hooke's law says F is equal to minus kx. So the force is equal to the spring constant times x is the elongation, how much that spring stretches or compressed. Later on in the year, we're going to talk a lot more about Hooke's law. We're going to talk about springs and stuff like that. So this just shows us how we can calculate the specific stiffness of a particular spring. But if we want to look at the energy that's stored in the spring, the potential energy stored in the spring, and sometimes they call this PES for spring, okay, that's equal to 1/2 kx squared. So it's 1/2 of the spring constant times how much that spring is either compressed or stretched squared. So there's also elastic potential energy stored in a spring. So that's 1/2 kx squared. And that's it for today as far as our notes, and now we're going to work some problems together.